Let us now talk about gravitational fields, the start of chapter 18. Let us first plunge into a historical rollercoaster of our understanding of gravity, for it was always understood that things fell to the ground, but understanding exactly why they would do so required the ancient Greeks. So the first offering came from Aristotle, though there are some indications that some people had developed some ideas before, but in his book, in Physics, and it is from his book that we get the name of the subject, by the way, about 400 BC in Athens, in his school, Aristotle made an observation. He noticed that heavy objects tend to fall faster than light objects. We now know that this is almost entirely due to air resistance, that if there was no air, then they would fall and accelerate to the ground at the same rate. But indeed, it is a valid observation that a heavy ball will hit the ground before a light feather. And they tried to fit this in to the understanding framework of the time of the four elements, earth, air, fire, and water, understanding that earth falls and fire rises, that objects that are hard and solid are attracted to the earth because they're of the same element. So you can see, even though some of the observations were valid, some of it didn't have the intellectual framework to allow those pieces of information to sit in a place where they made total sense. So in terms of if we knew certain things about gravity in 400 BC, why wasn't it until Galileo, over 2,000 years later, that much else happened in this field? Well, you have to know a little bit of history here. So what I've got here, and bear with me on this one, it's a map of the Greek Empire in 400 BC, and the orange spot represents Athens, if you know your geography, right there. Now, what happened with Aristotle was his works got passed on to his disciples, the people that learned from him and that would teach others in this sort of ancient way of learning, person to person to person. Now, one of his disciples took his works out to Asia Minor, in a place kind of where Troy was in even ancienter times, where they sat as the world changed, for the Greek Empire succumbed to the Roman Empire. And now, once the Roman Empire had spread, and this is a map of its maximum extent rather than perhaps exactly what it looked like at the time, those works were rediscovered in Asia Minor and taken back to Athens, where the value of them was recognized by collectors of manuscripts, where they then went to Rome. Of course, what happened is Rome fell. The Roman Empire collapsed, and what was Rome shrank into the east, into the Byzantine Empire. The works that were kept in those Roman libraries were taken out, and they ended up with book collectors in places like Baghdad. Now, as the Roman Empire crumbled away and fell, about 500 years later, what rose was the Islamic Golden Age, and those libraries in places like Baghdad and in such places were the only places where these texts were keeping. The very last library of the ancient Romans, and before that the ancient Greeks in Alexandria, was burned. And so basically physics, the book, ended up in Baghdad, where copies of it were made, and in the Islamic Golden Age spread to all of the places that Islam had spread, including into Toledo in southern Spain, where copies were made for the library. Now, 500 years ago, what happened is that turmoil in Spain changed who was ruling the place, and the Spanish kings took over from the Islamic parts of the country in the south, and Toledo's library was rediscovered, and from there the manuscripts in about 1500 could go out into the places where they could be studied, triggering the Renaissance. It was the discovery of those ancient Greek works, along with a few other things, that resulted in the world fundamentally changing in how it understood things. And so it is at this point, it is because the books bounced from library to library to library, it was at this point that the wider dissemination of those ancient Greek ideas got into places like Italy, where people like Galileo would work, over there into Poland, where Nicolaus Copernicus worked, and of course into England, where people like Isaac Newton would be working. All right, that's a little bit of histogeography over. Archimedes was somebody whose works also went through this journey. What we know of him is that he lived in Sicily, at Syracuse, and he lived at that time immediately before the Romans took over from the Greeks. It was a Greek colony, but as Rome grew and took over the Italian peninsula, the very last thing we know of Archimedes is that he died in the battle where the Romans invaded and took over Sicily. Now, Archimedes was instrumental in his understanding of gravity because for the first time he isolated something that we would call weight. He knew that objects had weight and it was a force acting downwards, and that something that floated had an upthrust equal to its weight. Now, his works also disappeared in that historical journey to places like Alexandria, and then copied to Baghdad, and then to Spain, and then back out into the wider world. So that 2,000 years later, in 1600 CE, Galileo Galilei, who didn't, as it happens, live in Italy. Well, he did, because it was Italy, but it just wasn't the country of Italy at the time. He lived in the country of the Grand Duchy of Tuscany, which was like a sub-country that eventually merged with all the other little city-states, forming what is today's Italy. So anyway, there he was, in Pisa, and in Florence and places like this. And as he was living his life, he made certain observations. And those observations included things that helped us understand how things fell. He thought that when Aristotle's observation that a heavy thing would fall to the ground heavier than a light thing, he thought that maybe it was the air that was affecting the lighter object. And the way that he thought about this was he realized it was only because it was traveling very fast through the air that the effect of the air was very high. And so he slowed it right down. He took a heavy ball and a light ball of the same dimensions but made of different things, and he made them roll down an inclined plane like a ramp. And he found that they went down the ramp at the same rate. They had little bells that went along, and because he lived at a very key moment in history, at the very first time when we could time anything. For another one of his inventions was realizing that a pendulum could be used as a stopwatch. Before that, we had no way of studying motion because we had no way of quantifying time. He found a way, and as a consequence was the very first person to discover motion in a modern way. He noticed that heavy balls and light balls went down the ramp at exactly the same rate. They weren't going fast enough for air resistance to make a difference to them. This was the starting block for our understanding of a real law of gravity. With Galileo, this idea in itself was not particularly that revolutionary, but it did set the seed. Some of the other things that Galileo did really caused some trouble. His support of Nicolaus Copernicus's idea that the sun was at the center of the solar system and providing evidence that backed that up got him into hot water with the Catholic Church in the country where he lived. Now, what had also happened at about the same time as Nicolaus Copernicus was the Reformation, the Lutheranism, that basically a branch of Christianity split away from the Catholic Church, and places around, especially places like England, as a direct consequence of people like Henry VIII split away from the Catholic Church. It meant that England was a place where ideas could be pursued, and so long as they didn't interfere with the monarchy, they could be pursued without ideological or religious suppression. So basically, it was the perfect place for Isaac Newton to be born. Isaac Newton was born at Woolsthorpe Manor in Lincolnshire in England at a time just after the Civil War. And so what happened was in the reign of Charles II, Newton was working and was sent to Cambridge, a boy genius, and in his time at Cambridge in 1665, the great and bubonic plague of London broke out, which spread to Cambridge pretty quick. The university closed as the epidemic spread across the country. Isaac Newton was sent to his home at Woolsthorpe Manor, and being now the only surviving member of his immediate family, he got the place to himself. and he would study day and night. He managed to take his books home with him, and he came up with the ideas behind what he would later publish in 1687 for his Principia. Now, the ideas that he formulated, he later said in life, inspired by the falling of an apple in his orchard, was the idea that that thing that made the planets go around the sun and the moon around the earth was the same force that would make an apple fall to the ground on the earth. He likened their centripetal force to the force of gravity, which is, we now know, is exactly correct. He also noticed and realized and was able to derive from basic principles that the gravity got weaker with 1 over r squared. It was an inverse square law. And though some people like Robert Hooke, about 15 years later, without being able to demonstrate how they'd done it, claimed that they too had found this same principle, this is not credible, that it was Isaac Newton clearly and was able to demonstrate it from basic principles about 15 years before. And so we associate Newton most strongly with the discovery of gravity. We remember, and we mock sometimes, as an apple must have fallen on his head for him to discover it. But it was, he said to a later biographer of his, that it was just by gazing upon apples falling in his orchard and then looking up at the moon and wondering whether or not it was the same thing that compelled the moon downwards in its circle around the earth that would make the apple fall. Fast forward 100 years into Georgian England, and this very interesting man, Henry Cavendish, he wanted to see how strong gravity was, and he considered that if all mass had a pull of gravity, then all he needed to do was to gain some very large masses and put some smaller, more movable masses nearby. So he suspended some lighter masses on something called a torsion wire. Now, a torsion wire will twist when a force, when a moment acts upon the torsion balance at the bottom there, twists it. And it twists it by a certain amount relative to the amount of force that is detected. So a certain amount of force will twist it by a certain amount. So it twisting a certain amount enables you to calculate exactly the scale of the force that's produced it. Now, what he did was he brought these two massive, heavy lead balls close to the torsion balance, and he watched it twist. And he was, for the very first time, able to calculate how strong the force of gravity was relative to certain masses and certain distances between them. He was able to measure something that we call the gravitational constant G, or big G. Henry Cavendish was a very interesting person. He's clearly, along with a lot of the scientists that we spoke to, what in today's world we would call neurodivergent. He was unable to make eye contact. He was unable to talk to women at all. He never went out and socialized. He spent most of the time just thinking and using his brain. Many of the things that he discovered were found later in his papers after he died, things that other scientists had themselves claimed as their own, and more likely just independently discovered after Henry Cavendish. We're going to skip Einstein for now, and we're going to study exactly what this thing, Newtonian gravity, actually is. So what do we know about it? Well, for a start, the things that feel it are objects that have mass in a Newtonian world, and the things that give it off, the things that create this effect, are objects that do have mass themselves, which, with the exception of things like light, is nearly everything that surrounds us. Everything that is that has a mass, that has a substance whose quantity could be measured in kilograms, all of these things produce a force of gravity. It produces a gravitational field, in fact, that everything in the environment around it would feel an attractive force towards the center of mass of the object creating the field. So that is exactly what gravity is. It's a force that is exerted on other objects with mass created by an object with mass. So it's just a natural force of attraction between any two normal objects. Amongst the other things that Isaac Newton did, he came up with his second law of motion. The idea in the special case where mass is the same, that the force is equal to mass times acceleration. Now this is quite useful because we can see that the force on the left is creating the acceleration on the right, tempered by how much mass the object has. Now, what I could do is I could divide both sides of that formula by mass. So I would have force divided by mass. The force per unit mass would tell me how much acceleration my object would have. Now, in any situation, anything that was being propelled along, the force applied divided by the mass that was being accelerated would tell us how effectual it was and how much acceleration, how much its motion would change. Now, this is exactly what gravity is providing to a small object in a gravitational field. The amount of force that is being applied divided by the mass of the object tells us just how strong the gravity is and how quickly the object will be accelerated towards the ground. So we define this particular acceleration, the acceleration due to gravity, g, as being equal to the force per unit mass. But you might say, hang on, is this dimensionally valid? That the acceleration due to gravity would have the units meters per second squared. But if g is equal to force per unit mass, then is it still equal to meters per second squared? Well, deconstruct it slightly. The units of force, well, from F equals ma, would be kilograms meters per second squared divided by the mass there, so it would be divided by kilograms. It would be kilograms meters per second squared kilograms to the -1. So the kilograms cancel out and you end up with just meters per second squared. That yes, newtons per kilogram are exactly equal to meters per second squared. It's valid. And we use G, the gravitational field strength, not just the acceleration due to gravity. If you see, it has this second name that we use in these particular instances where we want to talk about it in terms of the force per unit mass. Now this is how G is defined. The force per unit mass acting on a small object in a gravitational field. To understand the effect of gravity, we're going to draw field line diagrams. And here are two examples here. Now, what's important to remember is that these lines don't really exist. They represent the strength of the force and direction of the force that an object might feel. Now, one of the things that we would say, if we look at the example on the left, and remembering Isaac Newton's apple, which, by happy chance, weighs about 1 Newton of weight, placing that inside that gravitational field at any one of those places would have it fall straight down following the line of the gravitational field line. Now, the one on the left-hand side is a uniform field, that all of the lines are parallel to each other and head straight into the ground. On the right, we have a radial field, and you can see that these are no longer parallel to each other. They converge at a point inside that mass there. Now, the things to remember when we're drawing field lines is we must always draw them with a ruler if they are straight, and if it's a uniform field, we should try to endeavour to make sure that the distance between the lines is the same. So measure a centimetre between each one, top and bottom, so that they are strictly parallel and at right angles to the ground. You want to ensure that they are symmetric. The one on the right hand side, for every one up, there is one down, etc. You want to make sure it is symmetric because you are saying things about the strength of the magnetic field or the gravitational field by the spacing of field lines. So they also need an arrow to indicate the direction of the field, because these field lines, they demonstrate the shape, the direction, and the strength of the gravitational field. If we have a planet that has got a very massive inner part and a less massive outer part, like a gas giant, or if we had a planet that was just larger and all made out of gas, or if we had a very small planet that was rock, so long as it was spherically symmetric, then what we could do is we could just put a circle around it and say that everything within this circle is contributing to the gravity. It means that everything within that circle could actually be represented as all of the mass of that object, no matter what its physical distribution. We could say that if it was focused at a point in the center, for example, the planet disappeared and was replaced with a black hole, of the same mass but of infinitely small dimensions, it would exist at the center of the field, and it wouldn't change the field lines outside of that circle. And so what this means is that if we've got a spherically symmetric object of whatever mass distribution, we could replace it with a point source in the center, acting in the center of the same mass. And it wouldn't change the strength of the gravitational field. It would change nothing. So long as we drew a circle around it, we could basically say that the gravitational field would be the same at that same distance from that point source of mass as it would be from the center of the planet, so long as we were sufficiently far away from it. So why are things like black holes so dangerous? It's not that they have any more mass than the objects that formed from them, and this is skipping ahead slightly, but it's because that you can get closer to the places where the gravitational field is very strong. So if you look at these two diagrams, we've got a star on the right-hand side. You can't get close to the places where the field lines are getting close together because the surface of the star is in the way. Whereas if you shrunk the surface of the star and replaced it with all of that mass acting in a point source in the center, you can get to a place where the gravitational field is freaky strong, and at that point you're going to run into problems. Can we really say that the mass is acting like from a single place? Well, yes, we can, because Isaac Newton proved it in his Principia in 1687. He came up with something that we now call shell theorem, and he did it with geometry, and I wouldn't recommend, unless you're really committed, going into exactly how he proved it, because it is quite complex. But what is true, if look at my diagram at the bottom there, which is simpler, if you're stood at point P, you're being pulled towards all of the matter in that sphere, right? And what you would find is that the horizontal components of the arrow on the left, pulling you to the left, are exactly cancelled out with the horizontal component of the arrow pulling you to the right, which means all of the horizontal components to the left are cancelled out by all of the horizontal components to the right. And so you feel no pull other than straight down towards the centre. That's the easiest way to explain why we can say that having a mass in a planet is, for the sake of its gravitational field, exactly the same as having all of the mass focused at the centre of mass in the centre. Now, we will more formally derive this at another point, but you might be interested to know what happens to the strength of gravity as you either go up into the sky and leave the surface of the planet or go down deep underground. Well, underground, it is straightforward. From the centre of the Earth moving outwards, there is more gravity in direct proportion to the radius you are or the distance you are from the centre. It means, conversely, if you travel down, then the gravity recedes with 1 over r. But above your head, the gravity decreases with 1 over r squared. Again, we will derive this, so do not worry. But the key takeaway is that the gravity is strongest on the surface of the Earth. There's less of it underground and there's less of it in the sky. So we live in the zone on the Earth of the greatest gravity. Isn't that fun? But that idea that the gravity inside the Earth increases basically in proportion to the distance from the centre, means that we can find out exactly how much gravitational field strength that we have at various different depths. For example, if we're on the surface of the Earth, the gravitational field strength is going to be equal to the force per unit mass. Well, that force we could describe as our weight, the weight of which gravity is pulling us downwards with, and it's equal to mass times the gravitational field strength, just a rearrangement of the formula. If we're halfway down, we are half the weight that we were when we were on the surface, because basically the gravity has g is now g over 2. The gravitational field strength has halved. And in the very centre of the Earth, you would be weightless. It wouldn't be very pleasant because it would also be extremely hot, and you'd still be under enormous pressure acting down on you from the material bearing down on you in every direction, but you would be weightless. You would not experience any weight as a result of gravitational fields, though we would be still experiencing the huge pressure of the material all around you pressing inwards due to the gravity of that material at greater distances from the centre pressing down towards the centre. So as Isaac Newton sat in his orchard and watched the apple fall, he realized that it was a uniform gravitational field acting downwards. But the uniformness of this was because it was local to what was an apparently flat orchard. One of the issues with living on a sphere that is so large is that if you zoom into it enough, it appears locally flat. It is where we get the flat earthers and flat earth hypotheses from, is that as soon as you zoom into a circle, it looks flat on a local scale. But he realized if you zoom out of that, that the spherical nature of the Earth would be more readily apparent. And those lines that, those field lines that appear to go straight down in a uniform field are actually radial, all pointing into the center of the Earth. And so what is a uniform field on this scale is a radial field on a different scale. We've just zoomed out of our picture. Let's talk for a second about centre of mass. And we must do this because we must understand the difference between centre of mass and centre of gravity. And the bit of work that you might need to go back over here is the Archimedes work. So the work relating to moments and things like that. Whereas Archimedes, the baton was handed straight over to Galileo as they found themselves able to calculate where the centre of mass of an object is. So imagine this object here, n subscript I. It's just there, relative to where we are at P, at distance r from where we are. Now, where is the centre of mass of this system relative to us? Well, what we need to do is we need to take the mass of that object I and multiply it by its position relative to us, and then divide by its mass. And that would give us where its centre of mass is in relation to us, the r centre of mass. Now, for one object, that's kind of obvious, because if it is 5 kilogram mass at 1 meter away, then we'd be doing 5 times 1 divided by 5. The centre of mass is 1 meter away. That makes sense, right? But this formula is actually really quite powerful because it enables us to calculate for multiple objects in a system, multiple discrete objects, exactly where the centre of mass is. I would have to sum up all of the masses times their position and divide it by the sum of all of the masses, and it would tell me where the centre of mass is of the whole system. It's exactly the same physics as a moment question, if you think about it. So that is how we could find the centre of mass where there are discrete individual points of mass within the environment. If we have something which is not discrete but continuous, like the interior of a planet, then what we have to do is we have to integrate. We have to integrate, first of all, the mass comes out when we take that as 1 over m, the integral of r by dm, and this is how we would find the centre of mass. Now, I won't worry about that too much. It comes into things like further maths later on. In year 12, when we were determining the centre of mass of an object, you might have cut something out and put little holes in it and hung a plumb line on it, allowed it to freely rotate, and you drew the line straight down, and you did it 3 times, and you found the centre of mass of the object. And if you were encouraged to create a strange shaped object, you may have found that the intersection of those lines fell outside of the physical shape of the object. If you made a horseshoe, the centre of mass would be in the middle, in the space that is not occupied by horseshoe. And the age-old example of this is the Fosbury flop, that when you jump over something, you are propelling your centre of mass over that thing, and you can gain a slight advantage by forming a horseshoe shape, because your centre of mass does not need to be lifted so high, but your body will actually go higher as you jump over a high bar. Now, what is the point of all of this? It's just that basically the centre of mass may not be exactly in the physical centre of the object, but might be slightly different, and it depends upon what do we consider to be the object itself. You see, with the Fosbury flop, if I carried some heavy armbands and made my arms and feet heavier, then I might potentially be able to get other parts of my body higher, because my centre of gravity would relatively become even lower still. So it is important that the physical objects in the system will affect where the centre of mass is. If I was looking at the Earth by itself, the centre of mass most certainly would be exactly in the centre. But if I look at the Earth-Moon system, then is it still in the exact center? No, it is not. And here's a little task for you to do. You've got the mass of the Earth here, you've got the mass of the Moon there, and the distance between the two centers of these. If we were to weigh these like a moments question, what would be the pivot point where basically the mass times the distance to this pivot of the Earth is equal to the mass times the distance to this pivot of the Moon? Where is the pivot relative to the Earth? Go and work it out and tell me whether or not and how close to the surface of the Earth it is. What you're going to find is the barycenter, as it's called, the balancing point, the center of mass of the whole system, is not in the center of the Earth. It's actually somewhere in the line between the Earth and the Moon, but actually still quite close to the center of the Earth, just because of the enormous mass of the Earth. If we look at two planetesimals that are more similar in size, we actually find that the barycenter exists outside of both objects. It exists in the space in between, the center of mass of these two, Pluto and Charon, out there in the Kuiper belt. They have a barycenter that is in the space in between them. You can work out exactly where it is. Now that means that both Charon, what we would call the smaller one, it goes around and it orbits that center of mass, and so does Pluto. Pluto does a small oscillation around it because it's closer to the barycenter. Charon, a much larger oscillation, but both around the common center of gravity. It means that even in situations that we have the Earth and the Moon does not orbit the Earth. The Moon orbits the center of mass of the Earth-Moon system, and so does the Earth. The Earth also orbits that center of mass. Of course, it is a very tight circle on itself, one so small that we don't really notice it. Indulge me this little flight of fantasy. Imagine that your spacecraft is approaching the Pluto-Charon system, and just as it happens, and this is quite lucky, the major axis between the two dwarf planets is at right angles to the direction that we're heading. When we're so far away that we cannot resolve the individual forces coming from the two dwarf planets, our motion would be directly towards the barycenter, the center of mass of the system. But as soon as we got close enough that the spatial separation of these two objects became relevant to us, then we would then start to feel a force of gravity between the spacecraft and Pluto, and the force of gravity between the spacecraft and Charon. And the force of gravity to Pluto would be greater than to Charon. So rather than head straight for the center of mass, we would in fact follow a line called the center of gravity. And it's basically that the larger gravity of Pluto would actually then start to pull us away from that straight line towards the barycenter, and we'd go crash on Pluto somewhere. It's very important if you're flying past Kuiper belt objects. And so this is a really good way of introducing a different term, the center of gravity. The center of gravity and the center of mass are the same thing if an object is totally uniform. So if I have a perfect sphere, then the center of gravity is towards the center, because that is where the center of mass is. It's the direction in which gravity points, and it normally points towards the center of mass, but not in situations where the object is not uniform, where the object has clumps and bumps and various different things. Here, we've got a large mass buried under the ground, and at a large distance away from this, where the effects of the force it produces as a result of gravity is minimal, then we find that the field lines go straight down, pointing at the center of mass of the planet. But close to that object, we find a component of force acting alongside the force coming from the rest of the planet, and that force is at right angles to the direction of the force that goes straight towards the center of mass. We find the local center of gravity, the line of in which gravity acts, doesn't head straight towards the center of the Earth, but is pulled to the side slightly. And so this is what we would call the center of gravity in that position. And it only comes up in places where the field is not uniform. So a buried lump underneath the ground, a mountain to our left, or indeed as we head in the gap between the Pluto and Charon system, we start to follow a center of gravity that would pull us down towards Pluto itself. Now we can use this as a great tool for understanding things like what our Earth is made from. If we place a satellite, and indeed we have done, this is the Gravity Field and Steady State Ocean Circulation Explorer, it's a bit of a mouthful, in a very low Earth orbit around the Earth, we can find that as it is going along in its orbit, that if a large mountain range is in front of it, the spacecraft is pulled along slightly faster, and then as it goes past the mountain range, it is pulled back ever so slightly because there's a component of the force that is not acting straight down. There'll be a component acting forwards because the center of gravity would not be at right angles to the surface of the Earth. It would be slightly inclined, pulling the spacecraft forward. And then the opposite effect once the spacecraft has gone past those mountains. It enables us to find irregularities in the Earth's mass distribution, especially in its crust and upper mantle. Finding places where there are big clumps of heavy stuff buried under the ground that are not visible on the surface of the Earth. In fact, the gravitational field of the Earth is utterly dependent on these mass distributions. There are places where there are buried high-density rocks that create a region in the Earth's surface where the gravitational field strength, G, is slightly stronger than in other places, the mid-Atlantic ridge, because of all of that iron that has come up between the tectonic plates. That is a place where the gravitational field strength is really higher. Places where the gravitational field strength is really low, Indian Ocean, places in China, for example, there is not a large density of material underneath the ground there, and so the gravitational field strength is fractionally smaller. Very, very important, because the strength of the gravitational field strength determines the local sea level. Where the gravitational field strength is really high, the sea level is actually lower than in places where the gravitational field strength is much less. When we are looking at calculations of what is going to happen to sea level with things like global warming, it's important to remember that sea level is not constant across the Earth. The sea level varies with the gravitational field strength. And so we have to study things like the strength of gravity in different places of the Earth to get a handle and understanding on where our sea levels are and how they might change. We can also, with this thing, and we call it gravimetry, find such things as how much mass something has, how much mass the Himalayan mountain range has, which is largely constant. But one place where it's very interesting is we can find out how much mass of ice there is on places like Greenland. We could measure it 1 year, and then we could measure it another year, and then we could subtract the two to work out the difference. This is one of the major ways that we can find out the rate of melting of the ice in places like Greenland and Antarctica. We can find out the mass of it and see how it compares year on year. We can also find things that are buried in the ground, deposits of rocks or oil or such like. But here's a very interesting one. In Mexico, we found this ring structure buried on the coast there at a place called Chicxulub. Now, in the Yucatan Peninsula, this is. Now, what this actually appears to be is an impact basin from a large asteroid or comet, most likely a comet. And looking at the rocks, we think it's from about 65 million years ago, which coincides exactly to when the dinosaurs went extinct. Here, gravimetry has provided an additional piece of evidence to show that this was the place where the meteor struck the Earth and caused havoc and killed the dinosaurs. But we're not bound by the Earth. We could have a look at other objects in the solar system. In the Moon, for example, we can find regions of high gravity in places like the lunar mare, where lava has been brought towards the surface and then cooled in the large impact basins on the near side of the Moon. And on the far side of the Moon, the terrae, the mountainous regions, even though they are higher than the mare, there's not such a high accumulation of high density rocks in them. The anorthosite is quite low density in relation to the basalts that exist in the mare. And so therefore we can actually understand where the rocks are different and where they change by literally studying the strength of gravity as we fly over the lunar surface.